Record. All right. So tomorrow we're going to have our first term test during class. So I sent out a little reminder about it, but it's a pretty straightforward process, especially considering how small the class is. I don't think anyone's going to have any issues because I can actually like put links in the CrowdMark folder because I don't have to have different version numbers. So basically, like at 10:55, you should get an email from CrowdMark mailer, and it'll just say like join or click here to access term test 1. And then all of the questions are written into the CrowdMark page. So there's no PDF. There's only one file that you have to download on the from the CrowdMark page, and it's just a file with some R output that you have to utilize. Otherwise, all the questions are written on the page, so you can write your responses in any way that you in any way that suits you. So if you want to write them by hand and then take a picture of your solutions and upload that, that's fine. If you want to write them on a tablet and upload from the tablet, that's fine. If you want to type everything out and you can do the required mathematics in Word, for example, that's also fine. Whatever method works best for you is fine, as long as you can get the answers in there before 12:20 when the test is due. Okay, so you'll have the hour and 20 minutes, like the full lecture time to complete it. As I had said in my previous email, we'll go through the sample test today during our lab session so that you guys can review your answers. Hopefully you've had a chance to at least look at it and think about some of the problems. As I had mentioned before, I would describe this as very reflective. So this sample test will be quite similar to what you see tomorrow. The only difference, like, I guess, if you want to be very specific about it, is the sample test here had 5 questions on it. The actual test only has 4, but the content is exactly the same. So we'll work through this today. And then with whatever remaining time we have, I'll be available for questions. And if you have any questions for me tomorrow during the test, I'll be in the office hour Zoom room, not the lecture room. The reason for that is just I can speak to students one at a time because I'm able to control who comes in and out. So if you're in the waiting room and you have a question, just be patient because I might be with another student. Otherwise, I'll get to you ASAP. All right. Before we get started, does anyone have any questions about the structure of the test or anything related to any kind of like logistical questions, I guess you could say? Okay, cool. So we'll get started then. So again, we're just going to work through the sample test I posted on Friday. So there's 5 questions, 1, 2, 3, 4, 5. The material on the sample test and on the actual term test will cover lecture sets number 1 and 2. So the first question you can see here is basically a review of regression analysis. So this is kind of a throwback question to what we would have studied in Stat 378 and what you would have done on the first assignment. And then the remaining questions are all related to lecture set number 2. So a lot of questions about the exponential family and GLM framework. And the final question is sort of a thought experiment, like how would you structure or formulate a GLM? So we'll work through it in order. Obviously, you can do the questions in whatever order you want. Tomorrow, you can do multiple questions at the same time if you want. Doesn't matter, whatever works for you. I'll just work through it in order now because that seems like the logical thing to do. Okay, question 1. Solar thermal energy test was conducted and 29 observations were recorded. Using each observation, the total heat flux was modeled as a function of isolation. It was modeled as a function of isolation, position of focal point in east direction, and position of focal point in south direction. The output for the fitted MLR model is given below. Part A, state the empirical MLR model. Okay, so I'll write everything on the graph paper there, and I'll post the solutions after. So we want to state the empirical MLR model. In our R output, under estimate, we have the coefficients of the model. So the MLR model is basically just going to be, in this case, so this is 1A. So we're going to have y hat I is equal to negative 242.68695 plus 0.21004 for x1 plus 5.68694 x2 plus 3.778899 x3. 889? 8, yeah. x3. Okay. Can you guys read that okay? Is it too small? Okay, cool. All right, so that's all we need for part A. That's the empirical model. So basically just the estimated model given the R output. All right, part B, interpret beta hat 2. Okay, so our response variable is total heat flux in kilowatts. X2 would be position of the focal point in east direction in inches. Okay, so beta hat 2 is equal to 5.68694. So what we can say here is, as the position focal point in east direction, as the position of the focal point in the east direction increases by 1 inch, the total heat flux is expected to increase by 5.68694 kilowatts. All right. So that's a pretty standard interpretation. Oh, yeah, you're right. We can write it like that. Or we can drop the I. Yeah, let's do it like that. That is more correct for sure. Thank you for pointing that out. So yeah, for part B, this is pretty much the standard interpretation. Oh, actually, I missed something here. Pretty much the standard interpretation of a slope. The only thing I'm missing, so as the position of the focal point in the east direction increases by 1 inch, the total heat flux is expected to increase by 5.86894 kilowatts. Now, I forgot, this is an MLR model. So this would be true given all other explanatory variables are held constant. I almost forgot about that. That's very important because we're dealing with an MLR model in this case. So as we increase X2 by 1 unit, the slope or the response variable will change by the slope, but only if X3 and X1 are fixed. Otherwise, if you're changing 2 units at the same time, the response variable is going to be a function of both of those changes. Okay. Any questions? Okay. All right. Part C. Okay, so this is this is actually one of my favorite questions because I just like this question. Given y bar I, given the sum of yi minus y bar squared is equal to 14,681.93, construct an ANOVA table for the fitted model. So we are going to build an ANOVA table using only what's given to us in the output, which I think is kind of a neat problem because you can really see the connection between these. So an ANOVA table, if you don't remember, can be structured as follows. So we have source, degree of freedom, mean square, and F. We're not going to worry about the p-value, but we could include the p-value. Okay, so under source, we're going to have regression, error, total. Okay, and then remember that the degree of freedom and the sum of square, these things are additive, so we can add across the column. All right, so in the out, we're told in the question the sum of the squares of yi minus y bar. So this is actually SS total by definition. So this 14,681.93 would go here. Okay. Now, we're also given a few other pieces of information that we can plug in kind of wherever we would like to. For example, we're told there's 29 observations. So given that we have 29 observations, that would mean the degree of freedom total is 28 because that's just n minus 1. So that's another easy one to pick off. Okay, what else do we have given to us directly? Well, we also have the residual standard error and the associated degrees of freedom. This degree of freedom for the residual standard error is actually the DF error. So this is going to be 25, and that makes this equal to 3. Now, it's actually very easy to work out DF regression because DF regression is simply the number of slope variables in the model, right? So we have 1, 2, 3 coefficients. So that's another way of working that out. All right. Okay, now from the output, the residual standard error is actually the square root of the MSE. So the MSE is going to be 16.62 squared. Okay, so I'll just make a note here. Okay, and then that would be equal to a number. Just need to look that up real quick. Come on, R, load. Computer is so slow. Okay, so that's going to be 276.2244. Okay, so here we're going to have 276.2244. All right. Now from this point, it's easy to work out the remaining values. So we can start by getting SS error. So we know that the mean square is the sum of square divided by its degree of freedom. So that means that the sum of square error is going to be 276.2244 times 25, which is going to be 6,905.61. And then the sum of square regression is just going to be the difference between the total and that SS error. So that's 7,776.32. Okay, and then the mean square regression is going to be the SS regression over its degree of freedom. So that'll be 2,592.107. I'll just move this over a little bit. And then we can get the F value by dividing the MS regression by the dividing the MS regression by the MS error. So that's 0.375. All right. So that's our ANOVA table for this problem. At least it should be, assuming I didn't make any mistakes. Any questions? Oh, yeah. Good catch, man. As per usual, any mistakes that I make, I do on purpose to check if you're paying attention, which is the greatest cop-out in the history of teaching. All right. Okay, cool. At the 5% significance level, is there evidence that the fitted MLR model is useful? Okay, so only a 3-mark question. We don't need to go through the whole process here of actually evaluating the model. But the thing is, in order to do this, we will have to have some idea of what the critical value or the p-value is for this particular test, right? So, okay, first off, essentially what we're doing is we're running a significance test. So we are testing H0, the fitted model is useful, versus HA, the fitted model is not useful. Now, there's other ways that you can write this test. This is actually sort of like an ANOVA style test, in that what we're doing here is we're basically testing the null hypothesis that all of the coefficients are equal to 0 versus the alternative that at least one coefficient is not equal to 0. So let's, I'll give you the p-value for this. Okay, so this will be fairly representative of what's going to happen, or what in the case that you need something like a p-value or a critical value, you can assume for the quizzes that I'll give them to you. So let's assume that we had the p-value here. Okay. So the p-value, as you can imagine, is going to be quite small. So we'll say this is given. So since we're testing at the 5% significance level in this case, we can say, since p-value is less than alpha, we will reject H0. And then the key part of the question, given the conclusion, or given the decision about the null, is at the 5% significance level, the data provide sufficient evidence to suggest that the fitted model is useful. All right, any questions? Okay, an SLR model of the form y equals beta 0 plus beta 1x was fitted to this data set. Does the following R output give evidence that x1 is useful as a linear predictor of y? Explain. Okay, so this is basically the same, pretty much the exact same process that we just went through. So you can see here in the R output, we're actually missing the t value for the test, but we are given the f value. So we can run this, we can actually answer this question directly based off only the output. Now, the interesting thing here is that the p-value in the coefficient is pretty much exactly the same as the p-value we had for the MLR model. So here we can say, essentially like we did above, since the p-value, well, first off, let's just be clear what we're testing. So in this case, we are testing H0 beta 1 equals 0 versus HA beta 1 not equal to 0. Okay, so we can do this test in two ways, like I said before. The easiest way based off the output is just to pull the given p-value. So the p-value that's associated with the F statistic here is actually testing the exact same thing. It's just testing model usefulness. So this is, in the case of an SLR model, model usefulness is the same thing as the two-sided test about beta 1. So our p-value here is 0.002678. Right, so in this case, since p-value is less than alpha, we can reject H0. And then we would basically have the same conclusion given above. So at the 5% significance level, I'll just cheat a bit here and pull this, but yeah, the same conclusion in this situation. So given the p-value for the test of significance, we have evidence that the model is useful. All right. Oh, what the hell? All right, so that's question one. Like I said, just kind of a review of regression analysis based off of what we did on the first assignment and what we discussed through the first lab and whatnot. I'll fix that later. Any questions? Okay, so now we'll get into the stuff that's a little bit more new. Okay, so question 2. Suppose that y is distributed GIG with parameters ABP, where GIG stands for the generalized inverse Gaussian distribution. So we're saying that Y is a generalized inverse Gaussian random variable with parameters A, B, P, with B and P known and PDF given below, where KP is the modified Bessel function of the second kind. Show that Y belongs to the exponential family of distributions and is in canonical form. All right, so because B and P are known, we're going to find the exponential family formulation in terms of the parameter A. Okay, so that's the first hint. In terms of A. So because B and P are known, we can consider them constants. All right, so we have f of y given A, B, P is equal to A, B divided by P over 2, or to the power of P over 2, which is divided by KP of the square root AB, 2 times that. Okay, and then we have y to the P minus 1, e to the negative AY plus B over Y all over 2. All right. So we want to get this into the exponential family form. So to do that, we are going to take the exponent of the log of this function. That's correct, right? I don't remember these things off. Check this real quick, make sure I'm on the right thing. Yeah, exponent of the log of the function. Okay, where are we here? So we're gonna have the exponent of the log of f of y given A, B, P. Okay, so this is going to give us the following. F of y of A, B, P is equal to the exponent of, okay, so now we're just going to start applying log rules. So we're going to have P over 2 log AB minus 2 or minus log 2 KP square root AB plus P minus 1 log y minus 1 over 2 AY plus B over Y. All right. Okay, so now we can simplify a little bit. There's a few things that we can pull apart here. So A is the parameter of interest. So for the natural function B, we need to have A separated or we need A to be separated out into its parts. The same thing with C of A. And then we also want to separate the y's as much as we can to get them into their different components so that we know what is going to be A of y and what's going to be D of y. So we can do that. So here we'll have P over 2 log A plus P over 2 log B. There's nothing we can do with this part. Plus P log Y minus log Y. Minus A over, minus A over 2y minus B over 2y. Right. So therefore, A of y is equal to y, B of A is equal to negative A over 2, C of y, I believe that's the next one. Oh no, C of A. Okay, so C of A is going to be a function of A, and we can also include the other model parameters in there, and then D of Y will be a function of all the remaining Y terms. So for example, we can have C of A is P over 2 log A plus P over 2 log B minus log 2 KP square root AB. And then we would have D of A. Oh, no, sorry. No, C of A, D of Y. Yeah. Yeah. And then we would have D of Y soaking up the remaining terms. So that would be P log Y minus log Y minus B over 2Y. I think that gives us everything. Looks good. And then we can say, since A Y is equal to Y, the distribution is in canonical form. All right. Any questions? All right. Number 3. Suppose y is distributed exponential with parameter lambda. The PDF can be written as f of y given lambda is exp to the log lambda minus log y, where a of y is equal to y, b of lambda is equal to negative lambda, c of lambda is equal to log lambda, and dy equals 0. Find the expected value of y. Okay, so for part A, we have the expected value of y is equal to negative c prime lambda divided by b prime lambda. Yeah. Okay, so c of lambda is log lambda. So this is going to be negative 1 over lambda. And then b lambda is equal to negative lambda. So this will be over negative 1. Okay, so that means that the expected value is 1 over lambda. It's pretty straightforward. And then b, we want the variance of y. All right, so this is going to be b double prime lambda times c prime lambda minus c double prime lambda b prime lambda divided by b prime lambda cubed. All right. So b double prime lambda is going to be 0. So this first part is going to be 0 times c prime lambda, which is 1 over lambda. And then c double prime lambda is going to be negative lambda to the negative 2 times b prime lambda, which is negative 1. And then this is going to be divided by b prime lambda cubed. So that's negative 1 cubed. Okay, so this thing is going to be equal to negative 1 over lambda squared divided by negative 1, which is 1 over lambda squared. All right. And those are both correct. Any questions? All right. Numero 4. Okay, suppose y1 to yn are independently and identically distributed according to a Laplace distribution with PDF f of y given b mu is equal to 1 over 2b exp to the negative 1 over b absolute difference between y and mu, where mu is known. Suppose that the expected value of y is equal to exp beta 0 plus beta 1 xi. Give the 3 components of the generalized linear model associating y and x. Can y be modeled in a GLM framework? Okay, so we have f of y given b mu is equal to 1 over 2b exp to the negative 1 over b y minus mu. No. All right. We want to give the three components of the GLM framework about Y. All right. So we have a response variable that belongs to the exponential family that has to be in canonical form, a set of model parameters, and the link function. All right. So the starting point for this is actually going to be pretty much the same as the two previous exercises. Well, at least exercise 2. Okay, so we have to get this thing. It's going to be negative log 2b minus 1 over b y minus mu. All right. So in this situation, a of y is equal to the absolute difference between y and mu. So this is not in canonical form. All right. And then b of b is going to be equal to negative 1 over b. And then c of y is 0. D of b is negative log 2b. All right. So that's the first step. So we need to see if this thing is in canonical form. So we can write it in terms of the exponential family, but this isn't in canonical form. And the question says, can it be modeled in a GLM framework? So right off the start, we know it's not going to be able to. All right. So what else do we need here? We need to give a set of model parameters. So those are pretty much given to us directly. And then we need the link function. So we have the expected value of yi is equal to exp beta 0 plus beta 1 xi. All right. This means that g of, okay, so let's write, just for clarity. So we'll say the expected value of yi, which is the same thing as mu I, is equal to the following. So that means that g of mu I is equal to the log of mu I, which is equal to beta 0 plus beta 1 xi. All right, so the GLM framework has three components. One, so y is in exponential family, but not in canonical form. Two, we have to give our model coefficients. So here we have x. X is equal to x1 through xn. And beta is equal to beta 0, beta 1 transpose. Okay. And then 3, we have G is the log link. All right. Okay, so then the last part of the question is, can yi be in a GLM framework? Explain. So we we would say here, since yi is, sorry. Since the distribution of yi is in the exponential family, but not in canonical form, yi can not be modeled in a GLM framework. All right, any questions? All right, last problem. So consider the problem of predicting the number of trips per week to a grocery for a house, predicting the number of trips per week to a grocery store for a household based on the number of people in the household income, and the distance to the supermarket. Suppose a GLM is proposed to model this association. Oh, sorry. Okay, thanks, Jordan. What's cool? The fact that I keep making mistakes. Okay, so we want to, there's a few different questions here, right? So identify the response, identify the explanatory, suggest a distribution for the response and justify, give the linear component, give the link function. All right, so this question is kind of more of a thought experiment. It's, you know, just basically trying to determine if you understand what it means to set up a GLM, if you understand the components of the GLM. It kind of plays off the previous question where we would have written the framework down anyways. But what we're trying to do here is justify a model where we can predict number of trips per week to a store based off of these different factors. So we can start off just by knocking off a few of these easier problems. So the response variable is the number of trips per week to the store. It's going to be yi. Okay, so the explanatory variables are going to be those three: number of people in the household, income, distance to supermarket. Okay, so then we have number of persons in household household income and distance to store. Okay, so we'll call this X1I. Well, actually, we don't really need the I's here. We can just, for now, we can just declare them as variables. So this is going to be Y, X1, X2, X3. Okay, part C, suggest a distribution for the response and justify your choice. Okay, so we're counting number of trips per week to the store. Number of trips per week is definitely going to be a, like trips is a whole number value. You're going to take 0 trips. You're going to take 1 trip. You might take 2 trips. Like it's very unlikely, I think, you're going to see situations where the response variable exceeds 3 trips. So this would be considered a rare event in some situations. So I think the natural choice here would be a Poisson distribution with rate lambda, since we are counting in a whole number weekly trips to the store, and it is very unlikely the number of trips exceeds, let's say, 3. Okay. So we could consider Y to be a rare event. All right. Give the linear component and justify your choice. This is a tricky part. So we're going to model Y. So we're going to have the expected value So we're going to have the expected value of Y is equal to mu I. So rather, let's say the expected value of Y is equal to mu I. We will have a model G of mu I is equal to beta 0 plus beta 1 x 1I plus beta 2 x 2I plus beta 3 x 3I. Okay. So this is essentially all we really need to do here. We just need our response variable, or the function of our response variable, to be linear with the components. There's not too much else to say. Okay, so here, or our model is our response is now linear with respect to the model parameters. Not too much to say there, really. Like, we just need to get the expected value of yi to be linear with respect to the terms, and then we're going to have to apply some transformation to yi. Right. So in this situation, we'll have basically, when we set the model up, we could write g of mu is like inverse g of the linear component but we haven't actually declared G yet. So it doesn't really matter how we structure this as long as we have the linear component being linear with the response variable. Okay, now the tricky part is justifying the choice of link function. We're talking about modeling number of trips to the grocery store as a function of persons in the household, household income, and distance to the store. We're using a Poisson model, so we really only have two different choices for the link function. So the question then becomes, do we expect an increase in these components to lead to an exponential increase in the outcome, or would we expect the increase to be linear? And that to me is a difficult question to answer, not really knowing a lot about the factors that affect trips to the grocery store. My thought process on the matter based off of what I observe is that people don't tend to make multiple trips per week to the grocery store unless they live close to it. So distance to the store being smaller is likely going to increase the number of trips to the store. Household income, I don't think is actually going to play any role in the number of trips to the store. So it doesn't, if you go 4 times a week or if you go once a week, I'm going to assume you're going to spend the same amount of money either spread out across those trips or in one setting. Number of persons in the household is definitely going to increase how much you buy, but again, I don't see this really playing a large role in determining how many times per week you actually go to the store. Like, I guess it depends on other factors like preparedness, how well you construct menu items, or how well you construct your grocery list and this sort of thing. I mean, perhaps there's going to be very rare situations where you forget something important. I mean, that's certainly understandable, but I would be surprised if any of these components really had like an exponential or demonstrated an exponential increase in weekly trips to the store. So my inclination here, given the problem, would be to say G of mu I is equal to mu I, i.e. we will use the identity link. The reason is that none of these factors, well, I'll say I suspect. The reason is that I do not suspect that any of these factors will have a strong linear correlation with number of trips. That being said, I would certainly not expect the relationship between Y and X to be exponential. Therefore, given Y distributed Poisson lambda, the only option is the identity. I realized after finishing the statement that the first part of the sentence is kind of useless. So really what I should say is we will use the identity link. The reason is I do not suspect, maybe I'll just take this part out so it's a little more structured. The reason is that I would certainly not expect the relationship between y and x to be exponential. Therefore, given y is Poisson, the only option is the identity link. And like really, we could continue to carry this discussion on for quite a while. It's only worth 2 marks, so we don't need to say, make 7 or 8 different points. But I don't think the relationship is exponential. That's the first thing. So if I have g of mu where the response variable is Poisson, I have 2 choices, which are the identity function and the log link function. So I don't think it's going to be u is equal to exp to the linear component. So the identity link is therefore the only logical choice. And to be honest with you, I wouldn't really be surprised if this model wasn't overly useful, because I don't think, based off the description, that any of these are really going to play a huge role in the number of trips you take to the store. What I would suspect, though, is amount spent at the store would certainly increase with the number of persons in the household. I think that's undeniable. Now, whether or not that's linear or not, I'm not sure. And you could probably argue that y as a function of x3 might show something that's useful, but whether or not that coefficient for x3 is going to be a number in a high magnitude, I mean, there's only one way to find out, which would be to actually fit the model. But I suppose if you live really close to a store, like it's just across the street, that would encourage you to do smaller grocery store trips because it's not as far of a journey. But that's the only coefficient I think really we're going to find any information from, given the response here. So that's my rationale. And that's more or less, what the question is looking for is just, can you set up the model, and can you give, based off what you know about the structure of those models, can you give a reasonable explanation as to why you think you would have the following link function and what the linear component would be like, etc. Okay, so that's the sample test. That took just about an hour with explanation and whatnot for me to finish. So I think in terms of length, it's fair, because you'll have an extra 20 minutes to complete it tomorrow without anyone chatting at you. And yeah, any questions? All right, well, so as I said, I'll post what I've written up here for you guys to use as review. The test is tomorrow at 11, and I'll use the rest of the time in this lab to answer any questions if you guys have them, but otherwise I'll stop recording here. And if you guys don't have any questions, good luck tomorrow. I'll be available for questions during the test if you have any. And if I don't hear from you tomorrow, I will speak to you on Tuesday when we restart lecture and go back to discussing the logistic model. Okay, so take care if you're taking off, and otherwise, let me know if you have any questions.